In this problem, we are going to try to find the Laplace transformation of this function f of t right here. Now, if we were just to ask to find the cosine of omega t, all we would need is this. However, we have a t in here, and this t is going to give us some problems, where we need to take into account our t. And to do this, we are going to have to manipulate this part of our Laplace transformation before we even get to here. Keep in mind that cosine omega t to this is the Laplace transformation of cosine omega t. So that's the Laplace transformation for this. Now, since we have a t, again, we have to do something different. What I'm going to do is I'm going to say that our f of s is equal to the Laplace transformation of f of t, and this is totally legal because it's in the notes linked below the like button, and this is going to be equal to this. So we're basically just rewriting this, except we have the capital F with our s in front, and this is going to be our new equation. Now, the way I'm going to manipulate this is I'm going to take d of s from both sides. So we're not going to focus so much on this part in the middle right here. We're not going to focus on that. We're only going to focus on the f of s and the very right side, the integral. So I'm going to multiply both sides by d over d of s. So I'll make both sides d over d of s. And then I'm going to rewrite this. Now, in rewriting this, I've rewritten the left side. We're going to take the derivative of the right side with respect to d of s. So f of t is just going to be a constant here. Our e to the negative s of t, we're going to take the derivative of. Anything with e, when we take the derivative of e, it's just itself. And then because of the chain rule, we're going to have to multiply this by a negative, not s, but t. And then we're going to have our dt here. Now, if we multiply both sides by this negative, so we can cancel it out on the right, we are going to get this as our equation. And we can see that the only thing that differs in here is that we have a t. Well, we have our t right here. And the rest of this is just the Laplace transformation right here. So we've kind of solved for t. So when we do this, we are going to solve for this part now. So we're taking the Laplace of cosine omega t. The Laplace of this we know to be equal to s over s squared plus r omega squared. And then remember this being multiplied by our t. Well, our t is kind of equal to this. So we're going to multiply it by negative d over d of s. That means all we need to do is, just like we did over here on the right, is take the derivative of all of this right here. So if we take the derivative of this, we are going to use the quotient rule, I think it's called, f prime g minus f g prime over g squared. So f prime is just 1, g is g, and then we'll have a minus s, or g prime. We're taking the derivative of s, so we're just going to have a 2s, and since we don't have anything with our w squared, that's just going to become a 0. And this is going to be over our s squared plus omega squared, and this is squared. And this negative right here needs to come down too. So there's going to be a negative out front. We are going to have a negative, and then if we combine like terms, we're going to have a negative 2s squared. So we'll just have a negative s squared. We'll have a plus omega squared, and then s squared plus omega squared. All of this is squared. And then we're going to factor in our negative. So we are going to have an s squared minus our omega squared divided by our s squared plus our omega squared, and this is all squared. So this is going to be our answer. Now we just need to look for it, and we can see that it is C. So that's how you go about solving this problem. If you want more network analysis problems, there's a playlist in the description, and there's notes also in the description. Both are linked below the like button.